Testing, can you hear me? Um, okay. Hello everyone, can you hear me? I'm just making a few changes. Okay, so going to be reading the physics book again from OpenStax, and I will do the second chapter. Hold on. Right. So this is the OpenStax website. I did chapter one. I read the entire thing last stream. This stream I might do chapter two and maybe chapter three as well. Is there an answer key? Yeah, I should just open the answer key. Okay, introduction. Vectors are essential to physics and engineering. Many fundamental physical quantities are vectors, including displacement, velocity, force, and electric and magnetic vector fields. Scalar products of vectors define other fundamental scalar physical quantities, such as energy. Vector products of vectors define still other fundamental vector physical quantities, such as torque and angular momentum. In other words, vectors are a component part of physics in much the same way as sentences are a component part of literature. Okay. So scalars and vectors. Many Many familiar physical quantities can be specified completely by giving a single number and an appropriate unit. For example, a class period lasts 15 minutes, or the gas tank in my car holds 65 liters. A physical quantity that can be specified completely in this manner is called a scalar quantity. Scalar is a synonym of number, time, mass, length, volume, temperature, and energy are examples of scalar quantities. Scalar quantities that have the same physical units can be added or subtracted according to the usual rules of algebra for numbers. For example, a class ending in 10 minutes earlier than 50 minutes lasts 10 minus 50, 40 minutes. Two scalar quantities can also be multiplied or divided by each other to form a derived scalar quantity. For example, if a train covers a distance of 100 kilometers in 1 hour, its speed is 27.8 meters per second, where speed is a derived scalar quantity obtained by dividing distance by time. Many physical quantities, however, cannot be described completely by just a single number or physical units. For example, when the US Coast Guard dispatches a ship or a helicopter or for a rescue mission, the rescue team must know not only the distance to the distressing signal, but also the direction from which the signal is coming, so they can get its origin as quickly as possible. Physical quantities specified completely by giving a number of units and a direction are called vector quantities. Examples of vector quantities are displacement, velocity, position, force, and torque. In the language of mathematics, physical vector quantities are represented by mathematical objects called vectors. You can add or subtract two vectors, and we can multiply a vector by a scalar or by another vector, but we cannot divide a vector. An operation of division by a vector is not defined. Let's examine vector algebra using a geographical method to be aware of basic terms and to develop qualitative understanding. In practice, however, when it comes to solving physics problems, use analytic methods we will see in the next section. Analytic methods are more simple conceptually and more accurate than graphical methods. From now on, to distinguish between a vector and scalar quantity, we adopt a common convention that a letter in a bold type with an arrow above it uh, denotes a vector. Also, they're denoting it like this. For example, a distance of 2 kilometers, which is a scalar quantity, is denoted by d is equal to 2 kilometer, whereas a displacement of 2 kilometers in some direction, which is a vector quantity, is denoted by d with an arrow on top. Displacement is a general term used to describe a change in position, such as during a trip from a tent to the fishing hole. Displacement is an example of a vector quantity. If you walk from the tent to the hole, as shown in figure 2.3, the vector d representing your displacement is shown as an arrow that originates at point A and ends at point B. The arrowhead marks the end of the vector. The direction of the displacement vector d is the direction of the arrow. The length of the arrow represents the magnitude d of the vector. Here, uh, d is equal to 6 kilometers. Since the magnitude of a vector is its length, which is a positive number, the magnitude is also indicative by placing the absolute value notation around the symbol that denotes the vector. So we can write equivalently d is the absolute value of the vector d. To solve a vector problem graphically, we need to draw vector d to scale. For example, if we assume 1 unit of distance represented in the drawing by a line segment of length 2 centimeters, then the total displacement in this example represented by a vector of length d is 12 centimeters as shown in figure 2.4. Notice that here, to avoid confusion, we use d is equal to 6 kilometer to denote the magnitude of the actual displacement, and d is equal to 12 centimeters to denote the length of its representation in the drawing. So the displacement vector from point A to point B is indicated by arrow with origin at point A and end at point B. The displacement is the same for any of the actual paths. All of this is distance, all of this is distance traveled, but the displacement is like a fixed arrow. Suppose your friend walks from a campsite at A to the fishing pond at B, then walks back from the fishing pond at B to the campsite at A. The magnitude of the vector displacement from A to B is the same as the magnitude of the vector displacement d from B to A. It equals 6 kilometers in both cases. So we write, the scalar quantity from A to B is equal to the scalar quantity from B to A. However, the vector AB is not equal to vector BA, because these two vectors have different directions. In figure 2.3, this is 2.3. No, this is 2.5. This is 2.3. Vector BA would be represented by a vector with an origin at point B and an end at point A, indicating vector BA points to the southwest, which is exactly 180 degrees opposite to the direction of vector AB. We say that vector BA is an antiparallel to vector AB and write AB is equal to minus BA, where the minus sign indicates an antiparallel direction. So A, B, this is one direction, minus B, A would like from B to A. It's this vector, but in the opposite direction. Two vectors have an identical direction and are said to be parallel vectors, meaning they're parallel to each other. Two parallel vectors, A and B, are equal, denoted by A and B, if and only if they have equal magnitudes. If and only if they have equal magnitudes. Okay, yeah. And they're parallel as well. Two vectors with directions perpendicular to each other are said to be orthogonal vectors. These relations between vectors are illustrated in figure 2.5. So A parallel to B, A anti-parallel to B. Okay, A is anti-parallel to minus A is equal to B because their magnitude is the same. A is orthogonal to B. Vectors can be multiplied by scalars, added to other vectors, or subtracted from other vectors. You can illustrate these vector concepts using an example of the fishing trip seen in 2.6. Suppose your friend departs from A and walks in the direction to point B, but along the way stops to rest at some point C. Yeah, so from A to C. Located three quarters of the distance between A and B, beginning from point A. What is the displacement AC when he reaches point C? If he walks all the way to B, his displacement vector relative to A is DAB, which has the magnitude 6 kilometers and a direction of northeast. If he walks only 0.75 fraction of the total distance, maintaining the northeasterly direction at point C, he must be 0.5 DAB equal to 4.5 kilometer away from the campsite at A. So his displacement vector at the rest point C has a magnitude AC, which is 4.5 kilometers, and is parallel to the displacement vector. All of this can be stated succinctly in the form of the following vector equation. In the vector equation, both sides of the equation are vectors. The previous equation is an example of a vector multiplied by a scalar. The result, DAC, of such a multiplication is a new vector with a direction parallel to the direction of the original vector. In general, when a vector A is multiplied by a positive scalar, the result is a new vector that is parallel to A. Okay, because it's like one vector multiplied by a scalar. You're just increasing or decreasing the vector. The magnitude B of this new vector is obtained by multiplying the magnitude of A of the original vector as expressed by the scalar equation. In the scalar equation, both sides of the equation are numbers. Figure 2.2 is a scalar equation because the magnitudes of vectors are scalar quantities. If the scalar alpha is negative in the vector equation 2.1, then the magnitude B of the new vector is still given by equation 2.2, but the direction of the new vector B is antiparallel to the direction of A. These principles are illustrated in figure 2.7 by two examples where the length of A is 1.5 units, where alpha is 2. And the new vector B is equal to 2. A has length B as a length 3 units and is parallel to the original vector. When A is negative 2, the new vector has length 3 units and is anti-parallel to the original vector. So we have A, we have 2A, we have minus 2A. Okay, we have R, which is A plus B. And suppose you have a fishing buddy departs. Okay. Now suppose your fishing buddy departs from point A, walking in the direction to point B, but he realizes he lost his tackle box when he stopped to rest at point C. So he turns his back and retraces his steps in the direction towards the campsite and finds the box lying on the path at some point D, only 1.2 kilometers away from point C. What is his displacement vector AD when he finds the box at point D? What is his displacement vector dB from point D to the hole? We have already established that he rests at point C. His displacement vector is zero point 0.5 AB. Starting at point C, he walks southeast, which means his new displacement vector is CD from point C to point D and is anti-parallel to AB. So he goes back, goes to C, goes to B, and then goes back, right? Um, Figure 2.6. Why is the picture so far away? Its magnitude of CD is 1.2 kilometers. So his second displacement vector is CD minus zero point 0.2 AB. His total displacement AD relative to the campsite is the vector sum of the two displacement vectors AC and the vector CD. So AD is AC plus CD. AD is, sorry, AD is AC plus CD. CD is going back. The vector of the vector sum of two vectors is called the resultant vector, or for short the resultant. When the vectors on the right hand side are known, we can find the resultant AD as follows. In general, in one dimension as well as high dimensions, such as in plane or in space, we can add any number of vectors. We can do so in any order because the addition of vectors is commutative and associative. Moreover, multiplication by a scalar is distributive. So we have a vector here, we have a vector here. So multiplying this vector, multiplying just this vector, let's say by 1.5, it does increase the overall resultant vector. When adding many vectors in one dimension, it is convenient to use the concept of a unit vector. A unit vector which is denoted by the symbol with a hat, such as u hat, has a magnitude of 1 and does not have any physical unit. So that u scalar of u is 1. The only role of unit vector is to specify direction. For example, instead of saying vector AB has a dimension of 6 and a direction of northeast, we can introduce a unit vector that points to northeast as succinctly that DAB is equal to 6 times this unit vector. Then the southwesterly direction is simply given by the unit vector minus u. In this way, there's a displacement of 6 kilometer in the southwesterly direction is expressed by this vector. When vectors lie in a plane, that is, when they are in two dimensions, they can be multiplied by scalars added to other vectors or subtracted from other vectors in accordance with the general laws expressed by 2.1, 2.2, 2.7, and 2.8. However, the addition rule of two vectors in a plane becomes more complicated than the rule for vector addition in one dimension. We have to use the laws of geometry to construct a resultant vector, followed by trigonometry, find vector magnitudes and direction. This geometric approach is commonly used in navigation. In this section, we need to have at hand two rulers, a triangle, a protractor, a pencil. Okay, yeah. For a geometric construction of the sum of two vectors in a plane, we follow the parallelogram rule. Okay, I will just skip through this. So basically, because I'm already familiar with this, so basically, if you have a vector here and a vector in this direction, the sum of these two vector does not have a position, only magnitude and direction. So I can place it anywhere. So if I go this direction with this magnitude and then this direction with this magnitude, the sum of these two vectors is this vector here, this magnitude and this direction. So, but yeah, so when they say parallelogram rule, they're talking about uh, placing the vectors in the same direction. So sometimes because there's no direction, there's no position with vectors. Um, so sometimes they would represent vectors by placing all of them in the same position. For example, at the origin. So this plus this would give this using a parallelogram rule. By parallelogram, they mean they can do this and they can do this. So here is the parallelogram. From one corner to another is the resultant vector. Um, from the origin of the two vectors, we draw a diagonal that is the resultant of the two vectors. The other diagonal of its parallelogram is the vector difference of the two vectors. Alright, okay, yeah. So this plus this would give us this. And then A minus B, A, and then going in the opposite direction of B. So minus B. So like for example, we have this vector minus this vector. So this vector should be the, so minus of this would be in the opposite direction. Just, is there a way I can rotate it? Yeah. So we have this. The resultant vector is in that direction now. This is the resultant vector. So minus of the old vector plus the same vector before will give us this new resultant vector. So minus b plus a will give us this vector. Vector b plus a will give us this resultant vector. You have, oh, you have a, c, d, a, c, b, and the resultant vector is over here. I did not know OpenStax had this. A B? Is it like this? This is the sum of these two. How do I change? Yeah, anyways. Next. How long is this? Because the vector bit will be mostly revision. So I'm thinking of rushing through this. Okay. In a rectangular xy coordinate system in a plane, a point in the plane is described by a pair of coordinates xy. In a similar fashion, a vector A in a plane described by a pair of its vector coordinates. The x coordinate of vector A is called its x component, and the y coordinate of vector A is called its y component. The vector x component is a vector denoted by ax. The vector y component is a vector denoted by ay. Cartesian system, the xy vector components of a vector are the orthogonal projections, as illustrated in figure 2.16, of this vector onto x and y axis, respectively. In this way, the following parallelogram rule for vector addition. Each vector on a Cartesian plane can be expressed as a vector sum of its vector components. So ax, ay, and then ax plus ay give this resultant vector. It is customary to denote the positive direction of the x-axis unit vector I, the positive direction on the y-axis the unit vector j. Unit vectors of the axis at I and j define two orthogonal directions of the plane, as shown in figure 2.16. So ax is equal to the scalar value ax times the unit vector I. A by time defines the scalar value ay times the unit vector j. The vectors ax and ay defined by equation 2.11. Where is 2 point? Oh, here. 2.11 are the vector components of A. The numbers ax and ay define the vector components in 2.11 are the scalar components of vector A. Combining 2.10 and 2.11, we obtain the component form of the vector. So we have the any random vector, we can divide it into its component forms. So one parallel to the x-axis and one parallel to the y-axis. When we know the scalar components ax and ay of a vector A, we can find its magnitude and its direction angle theta A. The direction angle or direction for short is the angle of the vector forms with the positive direction on the x-axis. The angle theta A is measured in a counterclockwise direction from the x-axis to the vector. Because the lengths ax, ay form a right triangle, they are related by the Pythagorean theorem. Okay, so the length of this is the length of this. We can use the Pythagorean theorem. So the length of this square plus length of this square and the square root of the sum will give the length of this value. This equation works even in scalar components of a vector, even if the scalar components of a vector are negative. The direction and angle theta A of a vector is defined by a tangent function of the angle theta A in the triangle shown in figure 2.18. So the angle between the x-axis comes from the tangent. Tangent of A divided by x. Right. So we have a random vector. Let's call it A. You can divide A into two components, the x part and the y part. Ax and ay. And we have scalar of A. Let's just type A here. We have A. So A, it's then let's say there's a vector. Scalar of A is equal to scalar of A. No, no, no. Scalar of A is equal to this square plus ay square using the Pythagorean theorem. Square root like that. And vector A is equal to ax plus ay. And theta, why is it so fat? Theta hold on. Let me get my tablet out. It's harder to draw with a mouse. We have what just happened. We have theta A, and then I should just write it. Theta A tan of this is equal to the opposite over adjacent, right? There. I don't know why I accidentally changed the screen. Think this is better. Anyways, um, we have this. In many applications, the magnitudes and directions of vector quantities are known, and we need to find the resultant of many vectors. For example, imagine 400 cars moving on a Golden Gate Bridge in San Francisco in a strong wind. Each car gives the bridge a different push in various direction. We like to know how big the resultant push can be. Let us return to the right triangle in 2.18. This one. Quotient of the adjacent side ax to the hypotenuse a is the cosine function of the direction angle. Okay, so ax, a times cos ax. That makes sense. Ay is a times sine ay. So the length of this, let me remove this actually. We have so ga to a. So the sine, so yeah, sine is this, cos is this, tan is this. To describe locations of points or vectors in a plane, we need two orthogonal directions. In the Cartesian coordinate system, these directions are given by the unit vector I and j along the x and y axis respectively. When describing rotation, we usually work in a polar coordinate system. In the polar coordinate system, the location of point P in a plane is given by two polar coordinates. First is the radial coordinate, which is the distance of point P from the origin. The second polar coordinate is the angle phi that the radial vector makes with some chosen direction, usually the positive x-axis. In polar coordinates, angles are measured in radians. The radial vector is attached to the origin and points away from the origin to point P. The radial direction is described by a unit radial vector r. Okay, now we have a different coordinate system. Polar coordinate instead of x and y. If you want to describe a point P, we describe the distance from the origin and we describe the theta, r and theta. Well, it's not theta, it's phi. That looks ugly. Phi. So in the x and y plane, this would be, the x part would be just the x position, r cos phi. And then the y part would be r sin phi. No, no, no. Well, the vector px would be r cos phi, but the vector py would be r sine phi. Yeah, yeah. This r is a scalar, right? Yeah. The second unit vector t is a vector orthogonal to the radial direction r. The positive direction indicates how the angle changes in the counterclockwise direction. In this way, a point P has a coordinate system xy in a rectangular system can be described equivalently in the polar coordinate system by two polar coordinates. Which is in three dimension. We have I, J, and we have K for the Z direction. What just happened? Oh, when I click 2.11, it now registered. And then AZ is equal to ZE minus CB. Or the beginning of a vector and its end. Its scalar component are obtained by taking the difference AE dy are given by equation 2.13, and the Z component is given by this. Magnitude of A is obtained by generalizing to three dimensions. And generalizing 2.15 to three dimensions. Okay, it's like Pythagoras theorem, but for three dimensions. This expression for the vector magnitude comes from applying the Pythagorean theorem twice. Okay. Algebra of vectors. Vector can be added together, multiplied by scalar. Vector addition is associative and commutative. And vector multiplication by a sum of scalars is distributive. Also, scalar multiplication by the sum of vectors is distributive. In this equation, alpha is any number. For example, a vector antiparallel to vector can be expressed by simply multiplying a to scalar alpha is equal to -1. Generalization of the number 0 to vector algebra is called the null vector, denoted by 0. Okay. All components of the null vector are 0, so the null vector has no length and no direction. Two vectors A, B are equal vectors if and only if their difference is the null vector. Alright. This vector equation means we must have simultaneously ax minus bx, ay minus bi, and so on. Hence, we can write a is equal to b if and only if the corresponding components of vectors are equal. Okay, so each of their sides are equal. Then we have r, the resultant vector. You can get that by adding up the components. If we were to sum up to n vectors, when each vector is fk, I, j, k, the resulting vector would be this. Okay, we are just adding up all the vectors, adding up all of their components. The reason I'm rushing through is because I've already done most of this. In many physical situations, we often need to know the direction of a vector. For example, you may want to know the direction of a magnetic field vector at some point or the direction of a motion of an object. We already said that direction is given by a unit vector, which is dimensionless entity. That is, it has no physical units associated with it. When a vector in question lies along one of the axes in a Cartesian system of coordinates, the answer is simple, because then its unit vector or direction is either parallel or antiparallel to the direction of the unit vector of the axis. For example, the direction vector t, which is 5 miles then in the I direction, and is a unit vector. Uh, what? Oh, is a unit vector t minus I. The general rule of finding the unit vector v of direction of any vector is to divide it by its magnitude v. Oh, I see, I see. So a vector may have some length, like let's say a. If we divide, like let's say this has the length of 5, we can scale it, we can multiply it to scale it, or we can divide it. But if we divide it by its own magnitude, if we divide it by 5, we get a vector in the same direction of length 1. So we end up with a unit vector in that same direction. Product of vectors. A vector can be multiplied by another vector, but may not be divided by another vector. There are two kinds of products of vectors used broadly in physics and engineering. One kind of multiplication is a scalar multiplication of two vectors. Taking a scalar product of two vectors result in a number, as its name indicates. Scalar products are used to define work and energy relations. The scalar product A dot B of two vectors A and B is defined by the equation A and B. So AB cos phi. Where phi is the angle between the vectors. The scalar product is also called the dot product. In the definition of the dot product, the direction of the angle phi does not matter, and phi can be measured from either of the two vectors to the other, because cos phi is equal to cos minus phi. Oh, so they mean like, and it wouldn't matter if the angle is from A to B or from B to A. Also, if two vectors are orthogonal, if you have a vector over here and you have a vector that is orthogonal, then because there's a 90-degree angle, then the dot product would be 0 because cos 90 is 0. So the dot product gives a scalar value, the length of A times the length of B times cos phi. Also, another way of writing the dot product is to multiply their components. A dot B is equal to length of A, length of B cos phi, but it is also equal to AX, yeah, AX BX plus it with AY BY. Maybe if it's in 3 dimension, then AZ BZ. Okay. Let me take out the proof of that because we did this in the calculus chapter. So they're defining the vector. So this notation is like you represent each of the different components. So V is 3 dimensional. V1, V2, V3 is uh, it's the length in each of the directions. So length, the x-axis, length in the y-axis, length in the z-axis. A dot product. Well, in the other book, the math book, they first started with this definition and then they proved the other definition. So that's why what I did here. So this is the component wise definition. So you multiply each of the components. Let the it should be let the angle between the vectors be should be, let's say that the angle between the vectors is 90 degrees. Is less than 90 degrees. This means V, U, V minus U can form a triangle. So V, U, and from V to minus U. Hold on, I think this arrow is supposed to be facing the other direction, right? Plus V. Um, no, it's correct. It's correct. Plus V minus U. So starting from here, minus U is here, then plus V is here. Then we get this. According to the cosine rule from trigonometry, we get so this square plus this square plus this square minus 2 VU times cos theta. Since the square of the vector's magnitude is the dot product of that vector itself, we have this is equal to this times this. This, by the way, is from the component definition. So from this definition, if you square it, if you square the length of this, sorry, if you square this, then what am I saying? So let's say V1, V2, let's add V3 as well. The dot product with itself, you will be multiplying each component twice by itself. So the length of this is the Pythagorean theorem, right? But we already know this is equal to this. So can write it like this. So the length of this is square root of the dot product with itself. Yeah, so the length of this vector, voila, square root of the dot product itself, or you can write it like that. So this over here is written like this. And V minus U. So dot product has a distributive property. So all of this dot V minus all of this dot U. You can do it like that. And using the distributive property again, we can write V dot V minus U dot V minus V dot U plus U dot U. And then we are left with this. So this turns to this. Length of V square cancels out, length of U square cancels out. And my -2 will also cancel out. So we are left with this, which is the other definition. So this is the proof of this definition matching this definition. Yeah, anyways. Sure, we have distributive law. A dot B since scalar products of two different unit vectors of axis give 0 and scalar products of unit vectors with themselves give 1, there are only 3 non-zero terms in this expression. All right, I know what they're doing. So they're doing it the other way. So this dot product this, we have the distributive property. We get we get all of this. But I is 1, ij is 0, ik is 0. Similarly, jj is 1 and kk is 1, so we are left with ax, bx, ay, by, ac, bc. I should write this proof as well. Um, so, okay. The vector product of two vectors, the cross product. Vector product of two vectors, A and B, is denoted by A cross B and is often referred to as the cross product. The vector product is a product that has its direction perpendicular to both vectors A and B. In other words, vectors A cross B is perpendicular to the plane that contains vectors A and B as shown in figure 2.92. So vector A, we have vector B. A cross B gives a vector perpendicular to both of them. We calculate it by, the length of this, the length of the new vector is calculated by length of A times length of B times it by sine phi. According to 2.35, the vector product vanishes for pairs of vectors that are either parallel or anti-parallel because sine 0 is equal to sine 180 is equal to 0. Okay, if the two vectors are facing the opposite direction, then they won't have a cross product because sine 180 is 0. On a line perpendicular to the plane that contains vectors A and B, there are two alternative directions, either up and down. The direction of the vector product may be either one of them in standard right hand orientation, where the angle between the vectors is measured counterclockwise from the first vector. Vector A cross B points upwards. Okay. And vector B cross A points downwards. So vector A cross B is the opposite of B cross A. This is the anti-commutative property. So we have the Crookes-Skew right-hand rule. It's a common mnemonic used to determine the direction of a vector product. As shown in figure 2.5, a Crookes-Skew is placed in the direction perpendicular to the parallel that contains vectors A and B. So we have Crookes-Skew that rotates like this. So what this is mnemonic is first to remember which direction the cross product goes. So if the Crookes-Skew goes from B to A, the vector is at the bottom. Crookes-Skew goes A to B, the vector is on the top. Similar to the dot product, the cross product has the following distributive property. We have I cross J is K, I cross K is I, K cross I is J. Yeah, I'm rushing through this because I've already done this chapter. But all the torque and stuff, I want to do it in the respective chapters, like all the exercises. I want to do the next chapter as well. So, chapter 2, uh, conceptual questions. What's the difference between conceptual questions and problems? Okay, we have to explain. Okay, we have to solve like practical problems in the problem section, and conceptual question is like I have to explain what we learned. Okay, a weather forecast states the temperature is predicted to be -5 degrees the following day. Is this temperature vector or scalar? Scalar. Also, I should just open my answer. Suppose you have two vectors, what relative directions between them produces the resultant vector with the greatest magnitude? What is the maximum magnitude? I think that's when they face the same direction because, like over here, the resultant vector is the sum of these two. But if they're facing the same direction, I think the resultant vector would be the greatest in that direction. What relative direction between them produces the resultant with the greatest magnitude? What is the maximum magnitude? They said parallel, sum of the magnitudes. Uh, what relative direction between them produces the smallest? Oh, that's when it's like this. What is the minimum magnitude? Oh, no, not this. And it's anti-parallel. We are going front and then we are just going back. So the result is 0. Is it possible for two vectors of different magnitudes to add to 0? Is it possible for three vectors of different magnitudes to add to 0? Uh, yes for 2, no for yes for 3 as well. So this is an example of two vectors adding to 0, going from here and then going back. But for three vectors, let's say we went part of the decision, like halfway, and then the rest of the, uh, like let's say we go here and then here. So the result is 0. Question 7. Is it possible for two vectors of different magnitudes to add to 0? But this is impossible. This is possible as I just explained. When a 10,000 meter runner when a 10,000 meter runner competing on a 400-meter track crosses the finish line, what is the runner's net displacement? Can this displacement be 0? Explain. Yeah, if the track is round, the track finishes where it starts from, then the displacement is 0, right? Can a magnitude of a vector be negative? No. If two vectors are equal, what can you say about their components? What can you say about their magnitude? What can you say about their direction? If two vectors are equal, then their components would be equal as well, right? Equal, the same. Give an example of a non-zero vector that has a component of 0. I mean, if the vector is like straight up, then it has a y component, but the x component is 0. A unit vector of the x-axis. If two vectors are equal, what can you say about their components? When the components, isn't this the same question? What can you say about their magnitudes? Okay. Question 13, equal, the same. A unit vector of x-axis, they're equal. If one of the two components of a vector is non-zero, can the magnitude of the other vector component of this vector be 0? Yeah. Uh, this jump to 2.4. What is wrong with the following correction? Can you correct them? C is equal to AB. Well, you can't multiply. It has to be either dot or cross product. But since C is a scalar, it's better to write A dot B. I'm assuming that's what they wanted. And for B, it should be A cross B. Why does it? Okay. C cannot be a scalar. This is valid. C plus 2A equals B. No. Scalar plus vector gives a vector. So B has to be a vector. A has to be a vector. A dot B cross no. Either so A, it has to be A cross B. And then C has to be a scalar. There's no division with vectors. There's no division with vectors. Isn't I? No, wait. There is a division with scalar, but C has to be a vector. And over here, C has to be a vector as well. Okay, I wanted to do the next chapter, but I will end this stream. I will take a break and then I will start with the next chapter and some other in the next stream. Problems. A scuba diver makes a slow descent into the depths of the ocean. His vertical position with respect to a board on the surface changes several times. He makes the first stop 9 meters from the board but has a problem with equalizing his pressure, so he ascends 3 meters and then continues descending for another 12 meters to the second stop. I need to draw this. 2.5, 25 actually. Problems 25. So vertical position with respect to the board on the surface changes several times. We have a board, we have water, we have scuba diver. He ascends, wait, his first stop 9 meters from the board but has a problem equalizing. So he goes down 9 meters and then he ascends 3 meters. It has to be one third of this. Then continues descending for another 12 to the second stop. And then he continues going another 12 meters. From there, he ascends 4 meters and then descends 18. Um, Ascends 4, descends 18, ascends again for 7 meters and descends for 20 more, where he makes a stop, waiting for his buddy. Assume the positive direction up to the surface. Expresses net vertical displacement. So he descends 18, ascends 7. So he ascends 7. Then he goes down 24. Um, so I have a calculator with me. I should have opened this one as well. 9, actually it's negative 9, right? Negative 9 plus 3, negative 12 plus 4, negative 18 plus 7, then negative 24, negative 49. So negative 49. Um, let's do some other problem. A trapper walks 5 kilometers straight line distance from his cabin to the lake, as shown in the following figure. Use the graphical methods to determine the trapper's displacement directly to the east, displacement directly to the north, and sum up to its resultant displacement vector. The resultant is like 5 kilometer here, right? If the trapper walked only in the direction east and north, zigzagging his way to the lake, how many kilometers would he have to walk to get to the lake? 5 kilometer straight line from his cabin to the lake, as shown in the following figure. Use a graphical method to determine the trapper's displacement directly to the east. So directly to the east. We have 40 degrees here. So we have 5 cos 40. 5 times 5 times cos 40. It shows here 3.83. And the vertical is sine 40, which is 3.21. Now I will, hold on, cos 40. Right, let's see. To determine the displacement directly to the east, displacement directly to the north, that sums up to its resultant displacement vector. If the trapper walked only in the directions east and north, zigzagging his way to the lake, how many kilometers would he have to walk to get there? So 5 sine 40 and plus 5 sine 5 cos 40 is 7.04. Question 33. Yeah, 7 kilometers. 3.8 east, 3.2 north. All right, then I will end this frame here. Um, it for the vectors in the earlier figure, find A, B, C. So A is A cross F dot T. A cross F. The vector is out of the page, right? A cross F dot T. We learned how to calculate the magnitude of it, but we didn't. The cross product, I know how to do the cross product, but the thing is, did they actually go through it? They only showed the magnitude, right? They did not show how to calculate the cross product itself. Nope. So wait, so how are we supposed to do that question? For the vectors in the earlier figure, find A cross F dot T. A cross F dot T. But A cross F would give a vector that goes out of the page, I think, right? Or into the page. But if we dot it with D, it would be orthogonal to D as well. So wouldn't it just give 0? A would be 0. A cross F dot P cross D cross P. A cross F dot B cross T. Wouldn't this also be 0? Hold on, let me see. Question 6. Yeah, 0, 0. A dot F times it by D cross P. A dot F, that I can calculate. You have the magnitude of this times it by the cos angle in between. But D cross P. What is 37 plus 53? It's 90. So the magnitude of the cross product would be 20 times 5 times sine 90. which is just 100. And this over here, okay, so it's 100 in like the top direction, I think. B cross T. B, no, it's 100 going into the page. And if we have A dot F, A dot F, we have 10 times 20, 30 plus 30, right? 10 times 20. No, wait. These two are opposite. But cos 180 is 0. So 10 times 20 is 200. Then we got 100. We got 100 from here. End up with 20,000. Okay. Okay, yeah, I almost understand, but wait. Scalar has got product. If two vectors are 180 degrees apart, should their cross product be a negative value? What if the angle between them is 180? So they took phi. Phi is a number between 0 and 90. That product is a negative one number when 90 to 180, positive 0 to 90. So shouldn't this be negative 20,000? Or is there something I'm missing? So this dot this is negative 200. What about D cross B? So we have a scalar over here. What about this? D cross B. Yeah, but the cross product goes into the page. So we multiply it with negative 200. The vector will then go out of the page, right? So it will be positive 20,000. Okay. Okay, I think that makes sense. But I don't like the corkscrew thing. So I was thinking about I was using my hands at first. So basically, I was thinking, where did it go? Where's the picture? Yes. I don't like it when it does that. So we are from the A cross B. So if I use my right hand, A is the index finger, B is the middle finger, and C, my thumb, is going upwards. And if I switch my right hand, if I do this with the index finger pointing here, middle finger pointing there, then my thumb is downwards. Yeah, I would use the right hand rule for this. I was using right hand for the other one. So now if I go back, we have B in the index finger, D in the middle finger, and the thumb is going up. But they said D cross B. So D in the index finger, B in the middle finger. Now the thumb is facing downwards. So we have in the K direction, but it's going downwards. Okay, yeah, then the answer makes sense. Okay, I will end the stream here. And I will take a break, but I will come back uh, for the next chapter. Anyways, see you guys next time. Bye.